So what we're going to aim is to basically understand and decode what are the key concepts regarding the rational functions where the oblique asymptotes are involved. So first, what we're going to work on is when do we have the oblique asymptote. Now, before we go on to the oblique asymptote, let's just kind of work on the horizontal asymptote and vertical asymptote key concepts. So now, when you're talking about vertical asymptote, let's say if you got y equals to 3x minus 2 upon x squared minus 4. Now, for vertical asymptote, you equate straight away denominator to 0. So let's say if I got x squared minus 4, if I equate this to 0, I get the two vertical asymptotes. X is plus or minus 2. So when you're finding out the vertical asymptote, you can find out by equating denominator to 0. Now, more debate is about horizontal asymptote and vertical asymptote. Oblique asymptote. So firstly, understand where we have the horizontal asymptote. Now, horizontal asymptote exists when your degree of numerator is less than or equals to degree of denominator. So for example, if I have got a function which is 3x plus 5 upon x minus 2, or y equals to 8x plus 7 upon x minus 5. So 8x plus 7 upon x minus 5. Now, when you want to find out the horizontal asymptote, if your degree of numerator and degree of denominator is the same, so you can just take the coefficients as a horizontal asymptote. So like y equals to 3 is the horizontal asymptote here, or y equals to 8 is the horizontal asymptote here. So if your degree of numerator and degree of denominator is the same, you just take the coefficients of the leading term. So leading term is like here it is x, here it is x. Now, for example, even if we have, let's say, 3x squared plus 5x minus 7 upon x squared minus 8x plus 2. Now, my leading term here is 3x squared and x squared. So your horizontal asymptote, when you find, it is going to be y equals to 3 upon 1. So y equals to 3 upon 1 is your simply horizontal asymptote. The second case is if your degree of numerator is lower than degree of denominator. Here it has to be equal. What if I have something like this? Y equals to, let's say, 8 upon x minus 5, or y equals to 3x plus 2 upon x squared plus 8. What happens in this case? So all of these cases, wherever your degree of numerator is lower than degree of denominator, you will have y-axis as the x-axis is the horizontal asymptote. So y equals to 0 will be the horizontal asymptote. So as a shortcut, you can remember, if degree of numerator is equal, then you look at the coefficient. If degree is lesser, here if anybody asks, blindly you can write down y equals to 0 is the horizontal. Here y equals to 0. Whenever degree of numerator is smaller. Okay, so that's about the vertical and horizontal asymptote. Now, concept of oblique asymptote. When you're finding out oblique asymptote. So for oblique asymptote, what we have is generally when your degree is higher, when your degree of numerator is higher than degree of denominator. Now, for example, if you got y equals to x squared minus 2x plus 1 upon x plus 3 or something like that. So when degree of numerator is higher than degree of denominator, in this case, you have something called a slant or oblique asymptote. Now, first thing is that you should have the division skill. Now, always remember, whenever you have been given a rational function, try to write down this as quotient plus divider, remainder over divider. So quotient plus remainder over divider. This is your general structure. So if you have x squared minus 2x plus 1 upon x plus 3. Now, for example, if I have x squared minus 2x plus 1 and x plus 3 is out here. So you are going to take this as first you divide it, you get x squared plus 3x, then you subtract, cancel. This is going to become negative 5x plus 1, and then you take x minus 5 here, negative 5, so negative 5x minus 15, plus plus 16. So the same divider that we have got here can be, this expression can be written as quotient, which is x minus 5, plus remainder, which is 16 upon divider is x plus 3. So if you take LCM of this and simplify, you're going to get this as expression. So now, how do I find out oblique asymptote? Ideally, when you are finding horizontal asymptote as x tends to infinity or x tends to minus infinity, whatever your y is, that's your horizontal asymptote, or you can say oblique asymptote. So you get y equals to x minus 5 as the oblique asymptote, because when x tends to infinity, if I take x as infinity, this part, if I take x as infinity, this part tends to 0. You get y equals to x minus 5. That's your oblique asymptote. So whenever you take x as infinity and whatever your y approaches to, that's called as the oblique asymptote. So let us just try to sketch this graph based on this information and try to see how does this graph behave. So other stuff that we need to find out is certain stuff that we need is root. So for roots, we equate the graph to 0. So 0 equals to x squared minus 2x plus 1 upon x plus 3. This equates to 0. So you get x squared minus 2x plus 1 equals to 0. So you get x is 1. If you factor out, so you get there is a single root. Then to get the y-intercept, plug x as 0. You get y-intercept is 1 over 3, because 0 over 0 minus 0 plus 1 and plus 0 over 3. So that's your 1 over 3. So you got the root, you got the vertical asymptote, you got the y-intercept. Now go for the sketching. So this is your x and y axis. Then you draw the important stuff like your vertical asymptote, which is at x equals to minus 3. X equals to minus 3 is your vertical asymptote. Then oblique asymptote is y equals to x minus 5. Now see, you should know how to draw y equals to x minus 5 line. So y equals to x minus 5 when you draw, it cuts at y-axis at minus 5, and so y equals to x minus 5 is like this. It's a straight line like this. So x minus 5, and also you can see the x-intercept is at 0, 5. This cuts here at 0, minus 5. Now comes the roots. So roots are at 1. So 1 is the root, and y-intercept is at 1/3. This is 1/3 is the root, 1/3 is the y-intercept. Now you sketch the graph parallel to vertical asymptote as well as parallel to oblique asymptote. You know that you can't go below the x-axis because then you'll have two roots. And then here, if I draw the graph, I'll have another root. That's not possible. Here, if I draw the graph, here is another root, which is not possible. So where is the graph finally? In the other half is basically in this part. So let's say if I take, I'll just pick up this part. Okay. So that's here. Yeah. So when you're now trying to find out where is the graph basically, this part is not possible. This is not possible here. So only place where its graph is possible is basically in this, which is out here. So you can actually gauge and try to verify with the domain and range that you have for the question. Now with the domain and range, you can say, how can I find out the range? Now range, I know this point is y greater than 0, but I don't know this turning point. You can find out that turning point also using the basic concept of discriminant. So let us just try to find out. Let us just try to find out the range of this graph using concept of discriminant. So now, in order to find out the range of this graph manually, which is like one of the important skills. So how do I find out the range manually? So see now here what we've got is our function is y equals to x squared minus 2x plus 1 upon x plus 3. So what you do is basically cross multiply. First you cross multiply and get an implicit equation. So it will become xy plus 3y equals to x squared minus 2x plus 1. Now Now bring in every term one side. So let's say bring in every term one side, so it'll become so it'll become x squared minus 2x plus 1 minus xy minus 3y equals to 0. So you'll get x squared minus xy. So you have x squared, leave it as it is. Now collect the x terms together. So if I take minus common, it becomes 2 minus, so 2 plus y times x it will become, and then plus 1 minus 3y. So I'm basically trying to get a quadratic in terms of x and y. Now you do one thing is, you do b squared minus 4ac, because for x and y to be real, you discriminate, this quadratic must have a solution. Like if there exists a y value, there should be corresponding x value. So b squared minus 4ac is greater than or equal to 0. So you'll get minus 2 plus y, the whole square, minus 4 times 1 minus 3y, greater than or equal to 0. So you get a quadratic inequality. So you solve the 4 plus, this will become 4y plus y squared minus 4, and this will become plus 12y, greater than or equal to 0. Plus 4 minus 4 gone. You get y squared plus 16y, greater than 0. So if you solve the quadratic inequality, root at 0, minus 16 and 0. So here it is minus, plus, and plus. So you get the correct answer here, y greater than 0 or y below minus 16. So that's why you can see it's greater than 0, and this value, y value now you got is minus 16. So that's how you can figure out the range also for this particular rational function.